Electrical code requirements. The National Electrical Code, referred to as NEC, requires grounding systems to provide a low impedance path for fault currents and lightning strikes. Article 250 of the NEC provides general requirements for grounding, while Article 250.52 specifically addresses industrial grounding systems. Ground ring. The NEC does not explicitly require a ground ring around a building, but it does recommend using one as part of a comprehensive grounding system. A ground ring helps to distribute fault currents more evenly and reduce the voltage gradient around the building. Specific local requirements. In addition to the NEC, there may be local codes or ordinances that apply to electrical installations in Sanford, North Carolina. It is important to check with the local authorities to determine if any specific requirements exist. Consideration for PVC embedded conduit. While PVC conduit is non-conductive, it is still required to be bonded to the grounding system. This is done by using metal fittings and bonding jumpers at all conduit connections. Recommended approach. Based on the NEC and general industry best practices, it is highly recommended to install a ground ring around the building. This will provide a robust grounding system that meets code requirements and helps to protect against electrical hazards. To further elaborate on grounding systems as it pertains to electrical safety, let's consider a more in-depth view of the topic. The purpose of grounding is to provide a safe path for electrical current to flow in the event of a fault. This helps to prevent electrical shock and fire hazards. Grounding also helps to protect equipment from damage caused by electrical surges. The NEC specifies the requirements for grounding electrical systems. These requirements are based on the type of system, the voltage, and the location. The NEC also specifies the types of grounding electrodes that can be used. Grounding electrodes are typically made of copper or steel and are buried in the ground. The grounding electrode must be sized according to the size of the electrical system. The NEC also specifies the requirements for grounding conductors. Grounding conductors are used to connect the grounding electrode to the electrical system. Grounding conductors must be sized according to the size of the electrical system. The NEC also specifies the requirements for bonding. Bonding is the process of connecting all metal parts of an electrical system together. This helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. The NEC also specifies the requirements for ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electrical shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas. Grounding is an important part of electrical safety. By following the NEC requirements for grounding, you can help to prevent electrical shock and fire hazards. A ground ring electrode encircling a building or structure is a bare conductor that is buried in the earth. It is one method of creating a low impedance ground. Here are some key considerations for ground rings. The NEC section 250.53. She addresses requirements for ground ring electrodes. A ground ring must be buried at least 2.5 feet or 762 millimeters below the surface of the earth. A ground ring must consist of at least 20 feet or 6.1 meters of bare copper conductor not smaller than 2 American wire gauge. Ground rings are often used in conjunction with other grounding electrodes such as ground rods or ground plates to create a more robust grounding system. The purpose of a ground ring is to provide a low impedance path to ground for fault currents, surge currents, and lightning strikes. This helps to protect people and equipment from electrical shock and damage. Ground rings are particularly useful in areas with poor soil conductivity, where other grounding methods may not be as effective. When installing a ground ring, it is important to ensure that the conductor is in direct contact with the earth. The soil should be free of rocks, debris, and other materials that could impede the flow of current. The conductor should also be protected from corrosion. In addition to the NEC requirements, there may be local codes or regulations that apply to the installation of ground rings. It is important to check with the local authorities before beginning any work. Ground rings should be inspected regularly to ensure that they are in good condition and are providing adequate grounding protection. The inspection should include a visual examination of the conductor and the connections to the grounding system. The resistance of the ground ring should also be measured to ensure that it is within acceptable limits. If the resistance is too high, the ground ring may need to be repaired or replaced. A ground ring, when properly installed and maintained, is an effective way to provide a low impedance path to ground. This helps to protect people and equipment from electrical shock and damage. Now let's talk about PVC conduit and grounding. PVC conduit is a non-conductive material commonly used for electrical wiring. While PVC itself does not conduct electricity and therefore cannot be directly grounded, the NEC addresses how to properly ground and bond metallic components associated with PVC conduit systems. Here are some key points. Firstly, equipment grounding conductors are essential. Even when using non-metallic conduit like PVC, an equipment grounding conductor must be installed within the conduit along with the circuit conductors. This equipment grounding conductor, or EG, provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. Secondly, bonding at enclosures is needed. When transitioning from PVC conduit to metallic enclosures or equipment, proper bonding is crucial. Bonding ensures that all metallic parts are electrically connected to create a common ground potential. This minimizes voltage differences and reduces the risk of electric shock. Thirdly, bonding jumpers are important. Bonding jumpers are used to connect metallic enclosures, boxes, and equipment together to maintain a continuous ground path. These jumpers are typically made of copper or other conductive materials and are sized appropriately for the circuit. Fourthly, grounding electrodes are also necessary. The equipment grounding conductor within the PVC conduit system must be connected to a grounding electrode system such as a ground rod, ground plate, or ground ring. This connection provides a direct path to earth for fault currents, enhancing safety. Fifthly, metal fittings need grounding. If metallic fittings are used with PVC conduit, they must be properly grounded and bonded. This includes connectors, couplings, and other hardware. Failure to ground these fittings can create a shock hazard. Sixthly, isolated grounding receptacles can be used. In some sensitive electronic equipment applications, isolated grounding receptacles may be used to minimize electrical noise. These receptacles have a separate grounding conductor that is isolated from the normal equipment grounding conductor. Seventh, conduit fill considerations apply. The NEC specifies requirements for conduit fill, which is the percentage of the conduit's cross-sectional area that can be occupied by conductors. It is important to ensure that the conduit is not overfilled, as this can damage the conductors and reduce their ability to dissipate heat. And lastly, local codes must always be considered. Local electrical codes and regulations may have additional requirements for grounding and bonding PVC conduit systems. It is important to check with the local authorities to ensure compliance. By following these guidelines and adhering to the NEC and local codes, you can ensure that PVC conduit systems are properly grounded and bonded, providing a safe and reliable electrical installation. Remember that grounding and bonding are critical for protecting people and equipment from electrical hazards. Now let's talk about the NEC, or National Electrical Code. The NEC is a widely adopted standard for safe electrical installations. It provides comprehensive guidelines for grounding and bonding electrical systems. Article 250 of the NEC is dedicated to grounding and bonding and covers various aspects of these critical safety measures. Let's explore some key aspects. Firstly, there is the general requirements that define the purpose of grounding and bonding, which is to create a low impedance path for fault currents, minimizing the risk of electrical shock and fire. Secondly, system grounding is important. This section addresses the grounding of electrical systems such as services, feeders, and branch circuits. It specifies the types of grounding electrodes that can be used and the methods for connecting them to the system. Thirdly, equipment grounding is important. This section focuses on grounding non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and machinery. It ensures that these parts are at the same electrical potential as ground, reducing the risk of electric shock. Fourthly, grounding electrodes are also important. This section specifies the requirements for grounding electrodes, such as ground rods, ground plates, and ground rings. It outlines the minimum size and installation requirements for these electrodes. Fifthly, there is the grounding conductor. This section addresses the sizing and installation of grounding conductors which connect the equipment grounding system to the grounding electrode system. It provides guidelines for selecting the appropriate conductor size based on the size of the overcurrent protective device. Sixthly, bonding is also key. This section covers the bonding of metal parts of electrical systems, such as enclosures, raceways, and piping. Bonding ensures that all metal parts are electrically connected, creating a common ground potential. Seventh, methods of grounding are outlined. This section describes various methods for grounding electrical systems and equipment, including the use of grounding bushings, grounding wedges, and other approved devices. Eighth, there is special equipment. This section addresses grounding requirements for specific types of equipment, such as generators, transformers, and sensitive electronic equipment. Ninth, there are also separately derived systems. This section covers the grounding of separately derived systems, such as generators and transformers. It provides guidelines for establishing a proper ground reference for these systems. 10th, high voltage systems need to be grounded as well. This section addresses grounding requirements for high voltage systems, typically those operating at voltages above 600 volts. The NEC is a comprehensive document that provides detailed guidance on grounding and bonding electrical systems. It is essential for electrical contractors, engineers, and inspectors to be familiar with the NEC requirements to ensure safe and compliant electrical installations. Now let's move on to local codes. In addition to the NEC, local codes and regulations may have additional requirements for grounding and bonding electrical systems. It is important to check with the local authorities to determine if any specific requirements exist in your area. Local codes may vary depending on the jurisdiction and may address specific issues or concerns that are relevant to the local environment. For example, some local codes may have more stringent requirements for grounding in areas with high soil resistivity or in areas prone to lightning strikes. Local codes may also address specific types of electrical installations, such as those in healthcare facilities or industrial plants. It is important to be aware of the local codes and regulations that apply to your project and to ensure that your electrical installation complies with all applicable requirements. Failure to comply with local codes can result in fines, delays, and other penalties. To find out about local codes, contact the local building department or electrical inspector's office. These authorities can provide you with information about the specific requirements that apply to your project. You can also consult with a qualified electrical engineer or contractor who is familiar with the local codes in your area. In summary, grounding is a critical aspect of electrical safety, and it is essential to follow the NEC and local codes to ensure a safe and compliant electrical installation. Now let's talk about the types of grounding electrodes. Grounding electrodes are conductive objects that are buried in the earth and used to establish a connection to ground. The NEC recognizes several types of grounding electrodes, each with its own advantages and disadvantages. Firstly, there are ground rods. Ground rods are the most common type of grounding electrode. They are typically made of copper or steel and are driven into the ground. Ground rods must be at least 8 feet or 2.4 meters long and must be installed so that at least 8 feet or 2.4 meters of the rod is in contact with the soil. Secondly, there are ground plates. Ground plates are metal plates that are buried in the ground. Ground plates must be at least 2 square feet or 0.19 square meters in area and must be installed so that at least 2 feet or 0.6 meters of the plate is in contact with the soil. Thirdly, there are ground rings, which we have already discussed. Fourthly, there are concrete encased electrodes. Concrete encased electrodes, also known as UFA-grounds, are grounding electrodes that are encased in concrete. Concrete encased electrodes must be at least 20 feet or 6.1 meters long and must be encased in at least 2 inches or 51 millimeters of concrete. Fifth, there are building steel electrodes. Building steel electrodes are the metal frames of buildings that are used as grounding electrodes. Building steel electrodes must be electrically connected to the grounding system. The choice of grounding electrode will depend on the specific site conditions and the requirements of the electrical system. In general, it is best to use multiple grounding electrodes to create a more robust grounding system. Now let's move on to grounding conductors. Grounding conductors are used to connect the equipment grounding system to the grounding electrode system. Grounding conductors must be sized according to the size of the overcurrent protective device. The NEC provides tables that specify the minimum size of grounding conductors for different sizes of overcurrent protective devices. Grounding conductors must be made of copper or other conductive material. Grounding conductors must be protected from physical damage. Grounding conductors must be installed in a neat and workmanlike manner. Now let's talk about bonding. Bonding is the process of connecting all metal parts of an electrical system together. This helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. Bonding is required for all metal parts of an electrical system, including enclosures, raceways, piping, and equipment. Bonding conductors must be sized according to the size of the overcurrent protective device. Bonding conductors must be made of copper or other conductive material. Bonding conductors must be protected from physical damage. Bonding conductors must be installed in a neat and workmanlike manner. Now let's talk about ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electrical shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas. GFCIs work by monitoring the current flowing through a circuit. If the current flowing through the circuit differs from the current returning to the circuit by more than a few milliamperes, the GFCI will trip, cutting off the power to the circuit. GFCIs are very effective at preventing electrical shock. GFCIs should be tested regularly to ensure that they are working properly. Now, to reiterate, contacting the local electrical inspector in Sanford, North Carolina, is strongly advised to verify if there are any additional requirements or exceptions that apply to the specific site you are working on. Always prioritize safety in compliance with applicable codes and regulations.